So. Yeah, do you feel like going now?
Sure. Fine with me.
Okay, sure. So first of all, hi all. So welcome back to this the GAL webinar series, and also Happy New Year to everyone. This is also our first talk in the year of 2023. So today we are very happy to have Professor Stefan Grünemann from Technical University of Munich at Department of Computer Science to give us a talk. So he is also an executive director of the Munich Data Science Institute. And so his main research focuses on reliable machine learning for graphs and temporal data. And he is particularly interested in graph neural networks, which also happens to be what he is going to talk about today, and their applications to molecular modeling. And he's actually received the Best Research Papers awards at many top conferences like KDD, ECML, PKDD. So he previously received his PhD degree in the out of TH Aachen University in Germany in the field of computer science. And also from 2012 to 2015, he was an associate with CMU in the USA. He received a Google Faculty Research Award and a junior fellow at the German Computer Science Society. So please join me in welcoming Professor Grünemann to talk about his work on robustness of GNNs.
Thanks a lot. Thanks a lot for the very kind introduction. You already said everything essentially I wanted to say here. But yeah, I mean, I will talk about robustness of graph neural networks as announced. And this is a bit like, somewhat like an overview talk as well. So I hope you learned something from the short presentation. Okay. I guess in this seminar series, I don't have to talk about too much why graphs or networks are important. So I will skip this slide more or less completely. So, but you all know that graphs show up everywhere. And I also assume that you all know about graph neural networks. So I assume there was some talk at least about graph neural networks, which have shown you this great success of this new kind of neural network architecture in the different application domains, drug discovery, molecular design, and so on and so forth. So today, actually, I don't want to talk about all these new exciting advancements in graph neural network architectures, design, or expressiveness, which I guess we learned about also in the seminar before, but I specifically want to talk about robustness, as the title said. So the underlying question is indeed, are these machine learning models we have introduced essentially in the last years are reliable? And this is important for two reasons. And let me actually start with the lower one here. On one hand, in many applications where we use graph neural networks, they're indeed really prone to adversaries. So for example, humans which try to manipulate the underlying system. Think about, for example, recommender systems where GNNs are used, or knowledge graphs, for example. So these application domains, they are essentially interacting with humans, and humans try to manipulate their predictions potentially, and this is what we want to prevent. And on the other hand, but we're also interested in, in general, not just human adversaries, but in general, safe use of machine learning techniques. And we are specifically interested in so-called adversarial perturbations, meaning worst-case corruptions. And we want to make sure that our models also behave in the worst case, if we want to use it, for example, for sensitive, very secure applications, for example. So that's the fundamental question I want to talk about here. Are machine learning models for graph GNN specifically reliable? And just as a brief background, some of you might know the answer for like classic domains like images, for example, like object detection, let's say, or image classification, where we all know that we get very good results, very high accuracy. So here, for example, we can easily classify that as a stop sign. But it has also been well known now for many years that these models are actually also not robust, not reliable, meaning if we craft some perturbation, as you see it here, right, some noise essentially added to the image, which leads to the right image, which we as humans still classify as a stop sign, we can easily show that all the more or less state-of-the-art models, they can be fooled. They can, for example, now predict yield sign with very high confidence. right? It's not that the model becomes unsure, but it says, I'm very confident that this is like a yield sign, for example. And this is something, of course, which we want to prevent, these small changes leading to different predictions. So what we started to investigate actually now, we have 2023 already, right? So it's almost now 5 years ago. Actually, I guess it's more like 2 years ago, but roughly 4 years ago, it's almost 5 now, right? If you count the actual age of these numbers here. We wanted to answer this question for GNNs, right? So how do GNNs behave under such kind of perturbations? Because the interesting part of course, on GNN is that we also have the underlying structure involved, right? It's not just that we have, like here, it's a graph, right, where we have node features, right, like here, like some feature vectors. It's not only that we can have perturbations at these node features, right, but we can also see perturbations in the underlying graph structure, right? Edges get deleted or added, so to say, right? What we essentially wanted to understand is whether these models are robust, right, or a bit more technical, so to say, whether this margin here, so the difference essentially between the currently winning class, the green class, and here the red class, right, this margin, the difference here between these two guys, whether this switches, so to say, in sign, right? So here it's positive, and then if we, for example, do some perturbation, it might or might not become negative, right? So the red class is winning. This is, of course, again, what we don't want, right? We don't want that it previously is green, and after some small change, it becomes red as a prediction, right? So here we're doing node classification. I guess you're all familiar with this task, right? We are predicting essentially the label for these unlabeled nodes, essentially. So can this happen? Can this happen that the label essentially changes, that the margin becomes negative, so to say, after the change? This was the underlying question we wanted to answer back then, and which essentially started this research field. And I can tell you the answer, and potentially not too surprising now. Yes, unfortunately, it can happen. It's not robust. Graph learning models are also not robust. Here, I just want to show you one experiment because I want to actually focus on something else in this presentation, but just to give you motivation. So what you see here, I see there's some background noise. You can unmute mute yourself, please. So what you see here is you see some benchmark data set, the so-called Cori data set. You see here the different, every dot corresponds to a node in the graph. And if it's above the line, it's correct. So the margin is positive. If it's below the line, the margin is negative, right? So it's in the wrong classification. So this is for the original data. And then essentially what we did in this work simply is we slightly manipulated the data. So essentially we added a few edges or deleted a few edges in a specific way. So you can do it, for example, somehow randomly. You can do it based on other techniques. You can use also our attack technique. What I just want to show you here is essentially, unfortunately, you can indeed quickly change the result of this prediction. What it means, again, is you take a prediction for a node, you slightly change some edges, and all of a sudden it's below the line, the prediction becomes wrong. And as you see here, to a significant degree, right? Almost any prediction you can change, any node in the graph is vulnerable to these changes. What we felt was even more interesting back then was the following. Since we are in the graph domain, we know that all these predictions we are making, they are coupled together, right? It's not an IID setting, but essentially we're doing some kind of collective prediction, right? Meaning if we, for example, change something here in the graph, it might also have an effect on some other node in the graph, right? Because it's all coupled together. And indeed, we wanted to understand whether this also is something which is critical in these GNNs. And we call this so-called undirected attack. Essentially what we did is we wanted to change the prediction of a node, but we are not allowed to touch this node nor its neighborhood. We can just change the rest of the graph and see whether this changes or not. And unfortunately, the answer is even under this setting, we can still get wrong predictions. So you see still the performance drops from 90% to 67%. So a significant number of nodes can be fooled in their prediction, even though we are not touching this node itself, right? You can think about if you want to use it, for example, for fraud detection in a social network, right? You change the rest of the graph and then you get some other predictions for a specific node. So this is essentially the negative side, right? Graph learning models are not robust, they are not reliable. And this is what I said, what we started 4 or 5 years ago, and where lots of research has been done in the last couple of years to somehow solve or to at least lower this issue a bit. And this is what I want to talk about quickly today. So first of all, of course, the first question you should ask yourself if we have this issue is, how can we improve now robustness, right? This is a big issue. Small changes leading to a different prediction. So how can we make it better? And one simple idea, actually extremely simple, is to check how actually a graph neural network, or like a standard a graph neural network, often looks like, right? And you should all know this, I guess, right? So essentially, a graph neural network is more or less like, in the spatial setting, so to say, is aggregating over the neighboring information, right? So we have some learned representations in the layer, and then we aggregate my neighbor's information, including our cells representation, for example. And then this is the updated representation in the next layer, so to say. If you look at this like from a visual perspective, right, you can think about it like in one layer, we have representations of nodes, right? Usually, of course, higher dimension representation, but here just for illustration purposes. And then, for example, we are computing here the mean, right? This is some standard choice here, of course, some mean or weighted mean. The issue is, and this comes from classical robust statistic, we know that the mean is not robust, right? The mean is not robust with respect to outliers, for example. But it means if you have some adversarial manipulations in your data, you might see some adversarial representations for other nodes. And if we then use the mean as an aggregation function, the mean will shift to something else, right? So the mean is not a robust estimator in the terms of robust statistics, right? And this, of course, then leads to downstream problems, right? If we are now using this as our representation, right, here as the output, and then we passing this further and further, this can lead to problems in the prediction at the end of the day. So what is an easy solution to improve the robustness of graph neural networks is that we are replacing the non-robust aggregation function, right, the mean or the weighted mean, by a more robust substitute, so to say, right? And this is something which people have studied already years, right? So I mean, simple choices, for example, are the median or the medoid, for example. There are other versions of that. So one issue of this is, of course, they have to be efficiently computable because you want to use them inside of a GNN, and they have to be somewhat differentiable, right? But the underlying idea is we use some robust aggregation function. So in one of the papers, for example, we indeed used the median, or actually like a soft version of the median, which essentially is like interpolating between the mean and the median. And the equation is actually not important here. It's also not too complicated. But essentially, we're using the median because the median is more reliable or more robust with respect to anomalies, as I guess, as you all know, right? And indeed, here in this case, it really works. In this illustration, right, if you would compute the median or the soft median here, you are still then close to the actual mean, and you are not affected by these adversarial representations, right? So you're not drifting away with your representation, but you're staying close to the actual mean, so to say, the true mean, the clean mean. So as I said, so in this version, for example, you can then, with this temperature value, interpolate essentially between the sample mean, which is not robust, but which behaves usually nicely from the accuracy point of view, and the dimension-wise median, which is very robust, but might not lead to the best performance, so you can control this a bit. So does this simple change work, right? It means it's a super simple change. In principle, you can use it also for other architectures, not just for GNN. In any case where you have an aggregation, you can replace it by a robust aggregation. So we didn't analyze that here in this experiment, but we looked at this, of course, also in detail. But here you see the results for GNNs. Yes, it works. Replacing an aggregation by a robust estimator helps a lot. So what you see here is essentially some vanilla GCNs or GDC. So these are variants of graph neural network models. And here, for example, you see our technique, which is using this median estimator. It leads to much higher adversarial accuracy. So adversarial accuracy means the accuracy after attacking the data, right? So even though the data is attacked, we still reach here high accuracy, while these here drop in performance. So indeed, there is hope. That's the story here. There is hope that we can get better architectures. We can make better machine learning models, better architectures. We can devise better training schemes to be less non-robust, to improve robustness. That's possible. So here, for example, you see a second technique, which is called an SVD GCN, which essentially tries to filter out adversarial edges. And in this scenario, it also works quite well. Here, I want to make a short, so to say, a break. I want to give you one point which I feel is very important. I hope also important for your community, in the signal processing community, which is about proper evaluation practices, actually. Because what we have noticed is essentially that many publications have shown nice so-called defenses, or you can call it also techniques to improve robustness, principles, which all have shown extremely nice results, right? So you see here, for example, again, like this is a standard GCN, which obtains some specific accuracy under adversarial attacks. And then many literature has been proposed, like this SVD GCN you have seen from the previous slide, or our technique, which you also have seen, but many others have been proposed, which all have shown very, very nice results, as you see it in these plots, under various different scenarios. The issue is that in many of these publications, and this is here my message I want to convey to you, is that many of these publications are focusing on so-called non-adaptive attacks. So what are non-adaptive attacks? It simply means that these publications, they take an attack principle, so a manipulation principle, so to say, which is not designed for their specific model. Or put differently, so these are two famous attacks. These attacks were designed for GCNs, and people have taken the GCN attacks, so essentially these attacks, to evaluate the performance of their models. Okay, and you see already here the problem, right? So what people essentially did in many publications is they use, let's say, a GCN to find some perturbation, right? So we are optimizing essentially over the perturbations, over the graphs in our case, to find a harmful perturbation, and then they check how their model behaves for this perturbation, right? This is, of course, not the optimal case. What you should actually do is you should, of course, find the perturbation which is hurting your model, right? You look at here, you're maximizing the loss, right? We're not minimizing usually. In training, you're minimizing, but for a text, we're maximizing the loss. So you should, of course, maximize the loss for your own model and not for some proxy model, okay? And this here, this is what is called a non-adaptive attack. So the attack is not adapted to your model. And this is what is called an adaptive attack, what people should actually do, right? So we can look back at these tables here. So what I've shown you here is these so-called non-adaptive attacks, which people have, so to say, used in their publication. So they have used standard attacks not designed for their approaches. And I mean, in a live audience, I would now ask, what would you guess? How do these plots look like if we have adaptive attacks? If we have attacks which specifically are tailored to the specific approaches, of course, it will look very differently, right? So you see it here in dark blue. So the performance now for these models is dramatically lower. So for this approach, it's even so low that it's not on this plot anymore. It's somewhere at the very, very end here, right? So this is extremely important, right? So the difference between these two different, so non-adaptive and adaptive attacks is extremely dramatic. And of course, if you're interested in worst case perturbation, this is what all these techniques are interested in, you should use adaptive attacks because you don't know what kind of attack has been used in practical application, what kind of noise you are seeing in the practical application. So here you see really the big differences. And then you see a very different figure. You see, for example, also that some techniques, seemingly robust techniques, are even worse than the plain vanilla GCN, which you all know about. Okay. So first intermediate take-home message for this brief presentation. So GNNs are not robust. Doing some small structural changes to your data can change the predictions, which is not desired. So we need principles to improve robustness. But if you do this, please be also sure to do proper evaluation practices that you really see what is the benefit of this improved model. So what is the alternative, right? So what is the alternative to just having adaptive attacks or having a hopefully good feeling that the models are indeed better or reliable? The alternative is indeed that you derive so-called robustness certificates, which are guarantees, really. So what we're interested in and what we're doing a lot in our research group are deriving guarantees for the predictions you are getting. So essentially want guarantees that the prediction does not change under specific perturbations to your data, given a specific model. Okay, so for example, deriving guarantees in the form like, if you change 10 edges, let's say, in your graph, we can guarantee you that the predictions won't change. So this is a robustness certificate. Okay. And I want to quickly show you here also, again, like an overview of principles, how you can achieve such certificates. And indeed, and back then, so to say, right, 90, 20, 21, we started with two kind of strategies how to derive these certificates. On one hand, we have so-called white box certificates. On the other hand, we have so-called black box certificates. And let me quickly dig into these two. So what are white box certificates? So as the name says, white box certificates, they essentially assume white box knowledge, which specifically means they know what kind of neural network you're using and what are the weights of this neural network and so on and so forth. So they really take your trained model and they try to derive some certificates based on this model. Okay. How do they work? So what they usually are doing, these techniques, is that they're looking at this margin I've shown you before, right? So the margin which was positive before and negative afterwards, right, when we do the change. And this is essentially what you can also visualize, right? Think about you have like a two-class problem, right? Class 1 and class 2, and you have some prediction, right? The point is somewhere located here. And now you see the probability for class 1 is higher than for class 2. So it's class 1, right? And here you also see now the margin, right? The margin is essentially the difference between the two classes. So how does it help us for giving guarantees? So the core idea is whenever we're doing a perturbation to our data, we get a different prediction, right? Changing the data means changing the prediction. So in this illustration, it means we get here like this region, right? We change the input and then we land here. We change the input and then we land here and so on and so forth. So we get this region. So what we would be interested in theoretically is this so-called worst case margin. So what is the smallest possible margin we can get under perturbations? Right? This is the closest point to the decision boundary, so to say. Right? Why is this helpful? Because if this worst margin here is still above 0, we know that we are still on the same side of the decision boundary, still class 1. And when the worst case margin becomes negative, right, we know it's not robust, it's class 2, or can become class 2. Okay. So the main point is to show that the worst case margin stays above 0. And then we have a certificate. Then we get like guarantee about our model stability. Okay. What is the problem? The problem is that this is usually intractable to compute, right? You cannot usually compute this because this means we have to essentially optimize over this entire set of perturbations. And we have to essentially compute this margin for a nonlinear function, right? The neural network is a nonlinear function, so getting the margin is a nonlinear function, right? So we have to do essentially a nonlinear discrete optimization problem, which is not tractable. So what is the research about? The research is essentially that we try to find some kind of approximation. So for example, we can find some convex relaxation of this kind of region, right? We find here like a superset. And then instead of computing this margin, we compute a lower bound on the worst case margin, right? So the superset, of course, means it has a smaller distance here. And this, of course, is still helpful, right? Because if we now know that this lower bound is larger than 0, we still can get the guarantee, right? Because if this is larger than 0, and this is larger than 0, we have our guarantee, okay? And the main point, of course, is that this lower bound should be tractable to compute, that we can efficiently compute this lower bound. Otherwise, there is no benefit. But this then gives us a robustness certificate. So here just one example to show how it could look like in this whitebox certificate. So you can, for example, look at the graph models which are operating on personalized page rank. So essentially for the experts here, so the prediction for a specific node I for class C is essentially like you compute a page rank vector, a personalized page rank vector centered at a specific node I. Essentially, we are measuring how similar or how important other nodes are for this node, and then you're aggregating essentially the logits over for the specific class or over all other nodes. Essentially, it tells you if I have here predictions for class 1 and here predictions for class 2, I'm doing a weighted average then to make the final prediction for a specific node. Okay. So for some of you, this might look familiar. This, for example, includes label propagation, feature propagation, specific GNN models, and so on and so forth. Okay. So it's essentially like a page rank diffusion model. So why do I show you this model? Because here the actual problem becomes clear what we have to do, right? We have to compute the so-called worst case margin. Margin means we compute the difference between two classes, right? The true class and the other class, right? So this is our margin. And here, the worst case means we have to optimize over all perturbed graphs, right? So we're trying to find the smallest margin over all admissible graphs. So for this family of graph neural network models, the problem essentially becomes the so-called page rank optimization problem, right? We try to find the page rank, which links to a graph, which minimizes this objective function. Yeah? This gives you the worst case margin. And if this is larger than 0, then you have a certificate, a robustness certificate. So this problem still seems to be challenging, right? So you're all here graph signal processing experts. I assume you all know about PageRank then, right? So optimizing this function does not seem trivial, right? And it actually is not trivial, but as it turns out, you can cast this problem as a so-called Markov decision process. This is what we did in this publication. And then you can show that you can essentially indeed efficiently optimize this even in polynomial time, which is quite surprising because this is quite a hard problem. So there is a solution how to solve this margin computation efficiently, which I don't show you today, unfortunately. I don't have time for that. Okay, so again, take-home message. We have the possibility to derive certificates based on Whitebox certificates, which means we look at the specific problem class, so for example, PageRank models. And for these models, we can derive very tight bounds, lower bounds of this worst case margin, which can give us very tight guarantees. The drawback is that for every model you develop, so if you develop a new GNN tomorrow, you have to derive a new certificate, which is somewhat like a tedious work to do. So what is the opposite of this strategy? The opposite is we use so-called black box certificates, which essentially don't assume more or less anything about your model. And the idea is essentially that we do some kind of randomization, some smoothing. So some of you might have heard about randomized smoothing. And let me just give you again here like the big picture that you have something learned hopefully from this session. So the underlying idea again of a certificate is essentially, can we guarantee that the prediction here being panda for this x is also still panda when we look at some perturbed x prime, right? Any x prime around this center point, so to say, right? So this is usually not possible if we don't know what neural network we are using, right? So we slightly have to change our problem setting. So instead of doing this for the actual neural network we're using, we are doing it for a so-called smooth classifier. Smooth classifier essentially just means we're doing some kind of ensemble. So instead of just monitoring what is the prediction at this point, we're essentially adding some noise to our data, right? We are essentially adding, for example, Gaussian noise. And then for all of these different samples, we are monitoring what is our prediction. Okay, so most of the time, if you sample here some noise, you still get panda. Sometimes you get a gibbon, or sometimes you even get a cat, right? But most of the time, you still get a panda. Okay, so in some sense, smooth classifier is like an ensemble where you inject noise to your data, you augment your data by noise, and then you're monitoring what is the majority vote. Okay, and for this smooth classifier, we can indeed make some statements about the robustness even without knowing what the actual underlying classifier is. Okay, and indeed it links again to this idea of worst case, as you have seen before. So before we talked about this worst case margin, right, the smallest difference for a specific classifier. Now we somewhat change the view. What we are doing is we try to find a worst case classifier. Okay, since we don't know what classifier you are using, we are trying to find the least robust classifier, so to say. Okay, what does least robust classifier mean? It means essentially we have here our set of all classifiers which give you the prediction you are seeing here, right? 80% gibbon, 50% ape, 5% cat, let's say, right? Because this is what you know when you, so to say, query your model. When you query your model, you get these numbers. And now we assume we have a set of potential classifiers which fulfill this condition. Okay? And now we are optimizing over this set of classifiers and we're finding the least robust one. The least robust one means the classifier which gives you the smallest probability when you look at x prime, right? So x prime at the other sample, the perturbed one, and we want that this is no longer gibbon, but it gets a different label, right? So we're minimizing the probability for x prime while making sure that our classifier gets the same prediction for x, okay? So why is this helpful? If now this tells you the least robust classifier gives you 70%, no, then you still say it's fine, right? It's robust. It's still 70%, it's a majority. If the least robust classifier says, oh, it's only 10%, then it's not robust anymore, right? So the point is, if the least robust classifier is still robust, right? If this H star is still robust, then also your original model is robust, okay? So that's the underlying idea. We're optimizing over the classifiers here, essentially. Again, this might look completely complicated now, right? You have to optimize over a set of classifiers. But surprisingly, this optimization problem is indeed, again, tractable in certain cases. For example, if you just have like a standard Gaussian noise here and a standard classifier which is operating on continuous data. Or what indeed we did is, you can show that if you have like a classifier operating on discrete data, meaning graphs, right? A graph is usually a discrete object if you don't look at weighted graphs. But let's say you have a standard graph, edge or no edge is a discrete object. You can show if you're operating on discrete data, this optimization problem can be solved in a tractable way. And this is what we did in this publication, again, which I don't show you in detail here. But what you can do then is, since this problem is completely agnostic to the underlying classifier, you can now apply it to really arbitrary graph neural networks, to the original GCN, to GAT, for example, and to many, many other models, because the only thing you have to know is what is the prediction we are getting when we smooth our input, when we noise augment our input. When you have that, then you can make some guarantees. And here, for example, you see some results. So what we see, for example, here is like, we see perturbing attributes. So we also have binary attributes, for example. And you see here in solid, for example, when you delete specific attributes, so features, binary features, you make a 1 to a 0, so to say. You see, for example, that if we delete 10 attributes, we can guarantee that 50% of the predictions, for example, stay the same. Okay, and this is a hard guarantee again, right? This really is a guarantee. Whatever 10 changes you are doing, these 50% of the nodes, they will not change in the result. So if you're more interested in that, of course, you can check out all the details. But the take-home message, again, is black box means you can apply to any classifier, and in our case, for any discrete data classifier, including GNNs out of the box. But of course, as you can imagine, the bounds, the certificates might be less tight than these models because we just don't assume anything about our classification approach. But it still works very well. So these are the two extremes. White box certificates, full knowledge. Black box certificates, more or less no knowledge. So of course, a natural question is there something in between? Right? Is there something in between? Until a few months back, the answer was no. But luckily, now the answer is, since the last NeurIPS, the answer is yes, there is something in between, which we call Graybox certificate. So what do we mean by that? And this is something which I guess where it becomes, again, very interesting for graph researchers. So the idea we had in these works is, I mean, black box seems too rough of an estimate, right? Because often we have some knowledge. So for example, we have the knowledge that we're using a message pathing GNN, right? That we're aggregating somehow over our neighbors in some way, right? I don't know exactly, or I'm not interested potentially in how I'm exactly doing this, but I know I have a message pathing GNN. Or for example, we know about specific invariances, right? We know that GNNs, for example, are permutation invariant, right? Or we know that specific other models are rotation invariant and so on and so forth. So the idea we had is, can we exploit these invariances or these underlying properties being, for example, a message pathing GNN to derive better certificates, right? Stricter certificates, which are stronger, but of course, still being generally applicable, right? Because we don't want to have a new certificate for GAT, for GCN, or for whatever GNN you come up with tomorrow. We just want to know you're using message pathing principles, then you're good to go. The answer is yes, this also works. And I show you here like the intuition, why this actually makes sense, for example. So think about you have a graph, and again, you want to classify a specific node, right? You do node classification. So this node V is unknown, we want to predict the label. Let's assume these two nodes, they have been manipulated in whatever way, right? Someone hijacked the accounts and changed the features, right? What happens in the message pathing GNN? It happens essentially that so-called, we call it here adversarial messages, get so to say, passed along these edges, right? In one hop, they are here, and in the next hop, they are here, and then it can happen that the class changes from class A to class B, right? You have these adversarial messages passing along the graph structure, okay? So how can we get rid of this problem? We can use this idea of the smoothing. So before I said we are somehow like adding noise to our data, what we are doing now is the noise essentially deletes, for example, edges. Right? And if we delete edges, like this edge, for example, or that edge, for example, these adversarial edges, they are intercepted, right? It's no longer possible that this negative information we are receiving here is forwarded to node V, right? So deleting edges essentially intercepts the adversarial messages. And now we can combine this idea with the smoothing I've shown you before. So what we can do is now we can essentially sample various versions of our graph. In different graphs, different edges are deleted. And then we take essentially the majority vote, simply speaking, right, and see what is the prediction here, right? So essentially what we had before as noise becomes now this edge deletion, and edge deletion means the adversary messages are deleted. So this principle can be transferred now to this GNN work. And indeed, this works surprisingly well, much better than a black box certificate than before. So here, for example, you see that we perturb much more nodes. So for example, if we perturb 20% of the nodes in our receptive field, right, like, you know, in the GNN, if we have a two-hop neighbor, two-layer GNN, only can you, of course, use the two-hop neighbors, right? They only make sense. If we perturb 20% of these, for example, which is a lot already, then we can guarantee, for example, 25% of the nodes are guaranteed to remain stable. Usually you, of course, in much smaller regimes, right, you wouldn't perturb 20%, you would perturb, I don't know, 1% or 10%. So you are here, so you see that we can now give guarantees for many, many nodes based on this Graybox principle. One last point I want to show you here before I come to an end already, and we have enough time then luckily for discussion before I, as I said at the beginning, have to leave on time, unfortunately. Another principle you can exploit, this again links to this Graybox knowledge, is that in graph scenarios, we often do, as I already said before, collective reasoning. Collective reasoning means we do multiple predictions at the same time, right? We are usually not just predicting the label for a single node, but we do this for all nodes at the same time, right? And this is also true for many other tasks. For example, for image segmentation, you're not doing a prediction for every pixel, right? But you're doing it for the entire image, for example, right? So we have like a collective decision process, right? Where multiple predictions are done at the same time. Again, exploiting this knowledge helps you a lot. Why? Look at this image here, it becomes very clear. So a certificate, a standard certificate, which only cares about a single prediction, is weak in the sense that for every prediction you are doing, the worst case might be realized by doing different perturbations. It means, let's check whether this prediction is robust. No, it's not, because we could delete these two edges. Let's check whether this prediction is robust. It's not, because we could delete these two edges, and so on and so forth, right? So for every node, the certificate might say it's not robust because you can use these kind of perturbations. So it's doing this reasoning individually. However, in practice, we know we have to do this collectively, right? So an adversary who has a budget of, here in this illustration, 2 edges to remove, cannot do it differently for every node differently, right? The adversary has to make a collective decision, which 2 edges can I change to make the most harm overall, right? So the point is, it's much better, instead of individually certifying nodes, we can collectively certify what is the number of predictions that are simultaneously guaranteed to remain stable, okay? So the certificate is now something else. It says, you have a budget of X edges to remove or to add, how many nodes, overall number of nodes, remain stable, instead of how many individual nodes remain stable. In this collective reasoning, indeed, I mean, it's significantly better. So here again, some experiment on different data sets. Here we delete again attributes, as you have seen before, for example. This is the naive solution where every node is individually checked. And then, for example, we can say for 10 deletions, 40% of the nodes are guaranteed to not change the predictions. But if you do this collectively, you see it's 90%, right? It's orders of magnitude stronger, because in a collective setting, the adversary has to decide where to place its budget, so to say. And this, of course, also works then for structure changes. Here, for example, if you delete 200 edges, then we can guarantee that 50% of the nodes, for example, are stable. And again, 200 is a lot if you look at the data, which has 8K edges, right? From 8K edges to delete 200 already, this is a significant portion. So usually you are more in this regime, you get much higher percentages. Okay, already a quick summary, and then we have hopefully enough time for some questions and answer session. So graph neural networks are not reliable, and I can show you much more experiments, of course, if you're interested in that, in various fashions, under various assumptions about what we know about the model. They are not reliable, unfortunately. Luckily, we partially know how to solve this issue, how to improve robustness by other architectures, by better training principles, for example. But what I also, again, want to repeat is be careful with the evaluation when you work on this area. And lastly, make also sure to exploit the problem domain, meaning, for example, Graybox certificates where you know it's a GNN, where you know you do collective reasoning. This gives you very strong guarantees, very strong certificates where you can really rely on the prediction. So you have hard guarantees about the model stability. With this, I already want to end here. Thank you for your attention. Thank you for your time. And I'm very happy to answer some of your questions. Thanks a lot.
Yeah, thanks, Stefan, for the very interesting talk. So actually, I think we already have a few questions in the chat. So maybe I should read out the question and then you answer.
Sure.
Yeah. So the first question is from William. So he's actually referring to slide number 5. So which means you have to go quite a long way.
Yeah, sorry, too many animations.
That's okay.
Yeah. Okay.
Yeah. So he's wondering whether the attacks are designed for each node separately,
yes,
or is it a
question.
single config?
Yeah, I see the question in the chat as well. Excellent question, and I guess you asked the question before I mentioned the last slide, right? Because here in this example, right? I mean, let's experiment. Here it's designed for each node separately. Right, what I've shown you at the end is exactly this collective setup where you do this collectively for all nodes together. Excellent question, but here in this slide, it's for every node individually, indeed.
Yeah, so then second question from Mario's on slide 14 and 15.
Mm-hmm.
So here, So here the attack depends on knowledge we have for the victim, like black box and gray box and white box. So applying the right box, we are testing the worst case scenario. I'm trying to understand.
That's correct. It's completely correct. So what we are testing here, because we're interested in the worst case also means white box, right? We assume full knowledge about the architecture. Exactly. So that's always what we assume. Of course, if you do at black box attacks, then it looks differently. And of course, all the defenses are stronger in a black box setting, right? Because then the attacker doesn't know what model you are using. But again, as I said, we are usually interested in the worst case because I don't know what application you have in mind, right? So then the worst case, of course, is a safe solution, so to say. Yeah, and of course, the hope is if something is good in the worst case, it's hopefully also good in the non-worst case, of course. Exactly.
Yeah. So I think then the next comment is more or less like a clarification of the clarifications. So the next question is from Vesa. So is there any way to use active inference of MDPs to tackle adversarial attacks?
I'm not an expert on active inference. I guess I need some background on that before I can answer that question. Probably you can explain me that, and I would be super happy to answer the question.
Yeah. So would you like to unmute first?
So hello, thank you very much for the interesting talk. So in the active inference, actually, we want to first define some policies which can bring our desired observation in future. So it is not just behaving passively like most of the supervised learning methods, rather actively also interact in the environment. And this is actually the process that Markov decision process can be well modeled with it. And because you mentioned about Markov decision process, I was wondering if there is a systematic way that we can also use it for adversarial effects in graph neural networks.
Excellent question. So I understood the first part differently than the second part. So yes, true, we used here these MDPs to solve the attack problem. So here we're using the MDP, essentially the policy we are getting here tells us what are the changes we have to do, right? The changes the attacker is doing, right? This is how we use here the MDP. How I understood your first part, which would be actually more interesting, and I'm not sure about any work on that, is that we use it as a defense, so to say, right? So how should I behave such that the attacker is not successful, so to say, right?
Yes, so it is actually based on the prediction of the behavior of attacker.
Yeah, exactly. I'm not aware of any model which is using NDPs in that context, right? So interesting direction for sure. So here, as I said again, here it's used as the attacker, so to say, right? How should the attacker behave? Indeed. But an interesting point. I'm not aware of any of this. Might be that something is out there, but otherwise interesting to investigate for sure.
Okay, thank you.
Welcome.
Yeah, so then there comes a question from Peter Wick on like whether there's any significant difference when looking at graph level task, and is it also possible to quantify the magnitude of perturbation in that case?
So the answer is yes. It's also not. I mean, it's not a significant. There's also non-robustness in the graph level task. Unfortunately, I don't have the plot here. In this black box paper I've shown you, we did also experiments on the graph level task. So yeah, you see the same issue. I don't recall the actual magnitude, to be honest. So usually it's not too big, and also not in these graph level tasks. So if you do like graph classification, I assume, right? I mean, you mentioned regression. Regression, I guess we didn't test. I guess we tested graph classification, if I recall, but there shouldn't be a big difference. For regression, of course, you have to see what do you mean as a change, so to say, right? You would potentially measure the deviation in some numerical value, right? Because here we usually measure just correct or incorrect, so to say, right? A binary decision. For regression, there is no binary decision to make. So yeah, I mean, we did it on a graph level task, but I can't tell you the magnitude at the moment. But feel free to check out, it was this publication, or at least this publication, probably even more. This one here, this efficient robustness certificate for discrete data.
Okay, I see. Yeah, so next questions from Daniel. So have you also tested how algorithms like GraphSage, which sample only a specific number of neighbors instead of all similar to edge deletion? So how would that perform instead of GCN?
I guess not. I guess we didn't test it GraphSage. We tested GUT, for example, PPNP, GCN, GDC, but I guess GraphSage was not on the list, unfortunately. But it's a good point, actually, because now what you mentioned is sampling neighbors links a bit to what I said at the end, also like sampling these or deleting these edges, dropping these edges. What I can tell you, though, is random edge dropout is not really helping. I mean, you have to be careful, right? You can think about an architecture which is randomly dropping edges, right? Then you can also show that this is not robust. This is different to what I've shown you with the certificate, right? Where we're also randomly dropping edges, but we use it for a certificate. So you have to be a bit careful. So just random dropping edges doesn't help too much. So I can't really give a good guess how GraphSage will perform. So it might be better, it might also not be better because it's just randomly dropping neighbors.
I see. So yeah, I think that answers the questions. So so next one from Somia Deep. So like are the robustness guarantees you mentioned effective equally across various domains that use GNN, such as molecular modeling or social networks?
Okay, effective, you mean how large is essentially, how big is the budget, right? So a guarantee always holds, right? It's a guarantee. So the difference would be on some graphs, the guarantee is we can guarantee that you can do 5 changes. In the other setting, we can say we can guarantee that you can do 100 changes, right? So this is how I understand now your question. And no, they are not. I mean, it depends on the data for sure. And it depends also on the model, right? I mean, here you haven't seen it such a big, I have to scroll again. So here the difference is not too big between these models, but there is a difference between models and there is a difference between data sets, right? So here, this is essentially what I mean with the budget, right? So this is the budget. So you can change 5 attributes here in this case. Probably we can go back to the end, then it's nicer numbers. Here, for example, deletions. So for some data sets, of course, you can do more deletions. For other data sets, you can only do a few deletions. But you always get a guarantee, right? It's always like a hard guarantee that under this budget, it remains stable.
But that is specific. That in that case, that will be specific to the data and, for example, like the number of nodes too.
Exactly, definitely. I mean, for molecular data set, I would expect that very few changes will change it, right? Because few changes mean a lot in a molecular setting, while in a social network, it's not so dramatic, right? I mean, that's of course different.
So I think Faisal also has a question on the measure on complexity. And I guess she's talking about the complexity in computing the certificates.
If that's a question, I can answer it, sure. So what we try to do to make it feasible, I mean, they're all polynomial time, otherwise it wouldn't work. Specifically the last one, the black box one, they are super efficient. So what you usually just have to do is you have to sample multiple times your model, right? You have to do multiple inference steps. This might be costly, right? You have to do it 1,000 times, for example. But then what you do with these predictions, that's usually super fast. So the complicated or the expensive part is essentially getting this kind of ensemble, right? You have to query your model multiple times. That's the expensive part. But this is again like polynomial, right? Because I assume that your neural network can be computed in polynomial time usually, or I could even say in constant time. But this is here really the point.
I see. I hope that this is the question that she asked. Okay, so next one from Victor. So thanks for the interesting talk. Like, do you denoise the original graph in any of the settings that you proposed it, and so that you also recover the non-protected graph? And have you explored along this direction?
We haven't explored this. We haven't published that. that's the answer. And yes, you can do this. And you can show this also for image data. If you do this kind of denoising and then you do a certificate on top of that, that's usually stronger. Indeed, you can do this. Of course, for graphs, again, it's a harder problem, as you know, right? I mean, all these, again, like a discrete object, but it's possible, yes. But not what I've shown you here, nothing we have published yet.
Let's see. So I think we have a last question could be, so asking about whether the perturbation is ill-posted. So yeah, do you understand the question?
Not sure what you mean with ill-posed.
Yeah, so would you mind to elaborate a little bit more, Perigo? So feel free to unmute, please.
Can she or he still hear us?
Yeah, okay. So, well, anyway, I think we clear all the questions on the chat. So I think for the other audiences, if you have questions to Stefan, like, please feel free to unmute and just ask directly the questions.
Oh, hello. Can you hear me?
Yes.
Yes.
So I have another question. Like, it's related to this aggregation function that you choose to make the model more robust. Like, how much does that overlap to like the distributed optimization? Like, there is a lot of work on Byzantine robustness over there, and like, for instance, the median it's a starting point there already as well.
Yeah. And
like, we're still kind of aggregating messages, even though in that case they are the gradients that are computed in nodes, while here they are the actual embeddings.
I mean, it for sure relates to that, right? I mean, I guess you said it already a bit in your answer, more or less. I mean, I feel the aggregation, I mean, in general, right? There's now a general comment. The aggregation we are usually doing, right? They are non-robust, or the standard aggregation. We can devise various different principles, as you said, right? We can do what we did here, this more like robust statistics, or we can go completely different routes. But I guess it's definitely interesting to explore how these different aggregation functions behave under different properties, right? Robustness is just one property, but it's definitely connected. Fully agree.
Sir, are you able?
I don't know. I mean, I can't give precise theoretical answers how they are connected, right?
Are you able to listen me?
Yes, I can hear you now.
Yeah, that ill-posed problem which I said is a small change in the node value is leading to a larger change, and we know that such type of problems are called ill-posed problems. So in that sense, I have asked it that is it an ill-posed problem?
I see what you mean. I mean, my understanding of ill-posed is slightly different, but using your notation, then yes, I mean, but then any neural network is a bit ill-posed, right? Because you have these non-stabilities in any neural network, right? Some small changes are always leading to a dramatic change. I mean, but that's also the point, right? We don't want a neural network to be completely smooth, right? It's about smoothness. How flat is your decision? curve, so to say, right? And at some point you are changing class, right? And you don't want to do this potentially very slowly, but you want to have these dramatic changes, right? So I would not call it ill-post, but again, yes, in this sense, it would be ill-post. Small change in the input means large change in the output. But it's also true because they have different dimensionality, right? The input dimensionality is super high dimensional usually, and the output dimensionality is much smaller, right? Like classes were this, I don't know, pixels of an image or a graph, right?
Okay, thank you, sir.
Welcome.
Yeah, so I think we only have time for maybe one more question at most.
Yes. As I said, I have to leave for a PhD defense on time. I hope that's fine.
I think we can leave you some time to get a glass of water.
Yeah, I mean, well, yeah. So anyone want to ask the last questions, or we just leave it like that?
Excellent. Thanks a lot. I hope
Yeah,
you learned something in this short presentation. Thanks again for the invitation. And if you have any follow-up questions, you can just send me an email, of course, anyone here in the audience. So yeah, feel free to reach out to us.
Yeah, so please join me to thank Stefan again. And yeah, thanks for the very nice talk.